Welcome back, everyone. Today we're starting Chapter 2 in Bio 137. This is everyone's favorite chapter. I'm joking, of course, because this is chemistry, and the vast majority of students that come through biology really are not fans of chemistry. I would also fall into that category. Chemistry is my least favorite topic that I ever took in school. So I understand what students' minds do if they are not chemistry fans. And I will promise you that I will take it easy on you. There is some chemistry that we absolutely have to know for our course and going forward. I will cut out anything that we do not have to know. But the chemistry that we learn in Chapter 2 and that I cover in these next few lectures, you really do have to understand, and it's going to be very important that you ask questions when you don't understand. Once we get to the end of Chapter 2, chemistry is behind you as far as learning it. But everything that we cover in this chapter, you do have to understand because we're going to refer to it throughout Bio 137, into Bio 139, and into your programs. So if you don't understand it, you really have to ask questions. Otherwise, you're going to fall behind later on. So with that said, let's go ahead and get started. Here is our not really attendance question. Here is a set of questions, and again, like in the first few lectures, I ask that you try to answer these before going on, before looking at the answer, just so that you can get an idea of where you are in the class. First, a patient is lying in bed with their back to you. They're lying on their left side with their head to your left and their feet to your right. Their sternum, that's that hard bone in the middle of your chest, is blank to their navel. Use directional terminology there. And the second question, the stomach belongs to which level of structural organization? So go ahead and pause the video, try to answer those questions as best you can, and then let's see if you've got the hang of it. Okay. So first, a patient's lying in bed, their back's to you, they're lying on their left side, their head is off to your left, their feet are off to your right. Thinking about their sternum, it is blank to their navel. Well, a couple things to remember here. It doesn't matter what position you're in. It doesn't matter what position they're in. It doesn't matter if they're facing you, away from you, standing, lying. It doesn't matter. Remember, we always refer to the patient as though they are in anatomical position. So ignore all of that about the position that they're in. They are standing up, facing you with their arms at their side, their feet slightly spread, palms forward, eyes forward. Even though they're not, that's how you picture them. So thinking about that, the sternum is blank to their navel. Well, the sternum is above the navel. But we don't use the word above. We have some different terminology in anatomy and physiology. So the sternum is above the navel. We would say the sternum is superior to the navel. Remember, superior means above. And next, the stomach belongs to which level of structural organization? Structural organization was how each thing builds and builds and builds, starting from atoms and going all the way up to organism. Well, the stomach is an organ, so stomach belongs to the organ level of structural organization. Make sure you understand these questions. If you don't, study them a little bit. If you still can't make them make sense, reach out and ask me, please. So here's that chart of structural organization that we were just talking about. We saw this back in Chapter 1. Today, we are going to be talking chemistry, so we are starting over here. We will be talking about atoms and molecules in the next couple of lectures. And then once we wrap up chapter 2, we're going to have our first lecture exam. Going forward into chapter 3, we will talk about organelles and cells. And as we progress, we will continue to talk about larger and larger parts of this chart. So today, we're going to be talking chemistry, and we're going to be talking for the next couple of lectures about atoms and molecules, the chemical level. And to start talking, we're going to be talking about matter. What is matter? We've all heard that word before. Some of us kind of have an idea of what it is, but let's think about what the actual definition of matter is. Matter is anything that both takes up space and has mass. So something that takes up space, something that has mass, which isn't exactly the same thing as weight, but we can kind of think of it as weight. So it takes up space and it has weight, mass. If it fits both of those criteria, it is matter. So your pencil, a brick, a cup of water, the water that's in that cup, all of that is matter. But you don't have to see it, and it doesn't have to have a lot of mass. So the air that is in the room with you takes up space and has mass. So air is matter. And there are 3 states of matter. There's actually a lot more than that, and it's constantly changing. I think there's like 12 or 13 states of matter if you're a physicist. But in biology, really, there's 3 that we talk about. That's all that we deal with, really. And those are solids, liquids, and gases. And if I asked you what a solid is, you can give me all kinds of examples. Same with liquid, same with gas. But by definition, it's a little bit tougher for most people to give a real definition of what a liquid is, or what a solid or a gas is. So let's pause for a minute and think of an example of each of these. And we're going to define what makes them fit that example. First, solids. The table that you are sitting at, probably. That's a solid. Why? A solid, by definition, is something that has a defined size and shape. So if you come back tomorrow, that solid, that table, is going to be the same size and shape, unless there's somebody that comes through and busts it up, but that's not really what we're talking about. That table, that solid, is a defined size and shape. If you took that table out of the room that it's in and you put it in another room, it's going to be the same size and shape. If you took that table and put it into a box, it's going to still be the same size and shape. If you put it in a box of a different shape, that table is still going to be the same size and shape. Regardless of what you do to it, that table is going to be the same size and shape because it is a solid, and solids have defined size and shape. Well, what about a liquid? So now let's think about a really big glass of water. We're looking at the water here, not the glass. So water is a liquid. How is that different from a solid? It's easy to look at it and know that it's different. It's easy to talk about it and know that it's different. But by definition, what makes something a liquid? I think I said solid a moment ago, but it's easy to know that that water is a liquid. So why is it? Liquids have a defined size. We say they have a defined volume. So they have a defined volume, but not a defined shape. They take the shape of their container. So back to our glass of water. Let's say there are 2 cups of water in that glass that you're holding. That water, the volume is 2 cups. The size, that's the 2 cups. But it's going to take the shape of the glass. Let's say your glass is round. Well, that water is going to fill that round glass up to 2 cups. Well, now we have another glass, but this one's kind of oval shaped. If we pour the water from the round glass into the oval glass, the shape of the water changes, but it's still got the same volume. If I pour the water out onto the ground, there's still 2 cups of water, but it now has a different shape. So liquid has a defined volume size, but it does not have a defined shape. It takes the shape of its container. Lastly, a gas. What makes something a gas? Gases typically are not visible, so they're a little bit harder to kind of wrap our head around sometimes. Some gases are visible, but the room that you're in right now is filled with a gas. You can't see it, but it is filled with a gas. So, what makes something a gas? A gas has neither a defined shape or volume. It expands to fill the size and shape of its container. So let's say that again. A gas has neither a defined shape nor volume. You can compress gas, or gas will expand. You could pump all of the gas out of the room that you're in and pump it into a very, very small container. It expands when it's in the room that you're in so that it fills the size and shape of that room. You pump it into a very small container, it's going to be compressed, and it will be in the shape of the container that it's in. If you burst that container open, the gas will then expand to fill whatever container it's in now. So solids, defined size and shape, or defined volume and shape. Liquid does not have a defined shape, but it does have a defined volume or size. Gas has neither a defined volume or shape.
All right, so let's switch gears here a little bit, and now let's talk about energy. And energy is a word that all of us have heard, but really most of us actually don't know the true definition of energy, and it gets misused a lot. Energy, by definition, is the capacity to do work. And that's all that energy is. When you hear someone has a negative energy or has a bright energy about them or something like that, that's not what energy means. That actually doesn't mean anything at all. Energy is the capacity to do work. And there's 2 types of energy. And here we're going to see in the next couple of slides that there's some really nitpicky terms, but they're actually very important. And right now we're going to learn the word type. And in just a little bit, we're going to learn something else that seems similar, but is actually not. So energy can come in 2 types: kinetic energy or potential energy. Kinetic energy is energy of motion, and potential energy is stored energy. And we can convert between those 2 types. We can go from kinetic to potential, or from potential to kinetic, as we'll see in just a moment.
So what we see here with my amazing artwork, there is a ball at the top of the hill, and this red thing is a wedge holding it in place. Now, the ball has energy stored inside of it. And that energy that's stored inside of it is potential energy. The ball could potentially roll down the hill, but it's not, because this red thing is a wedge and the wedge is holding it in place. So the ball has the potential to roll down the hill, releasing some energy. But, like I said, it's not rolling down the hill because the wedge is holding it in place. But we said that we can convert between two types of energy. So that implies that we could convert that potential energy into kinetic energy. Potential energy, stored energy. Kinetic energy, the energy of motion. So how do we convert that stored potential energy into kinetic energy, energy of motion? Well, what happens if we remove this wedge? Well, the ball is now going to roll down the hill. The ball is going to be in motion. The ball is going to now exhibit kinetic energy. It is in motion. So the ball rolls down the hill. It releases all of this kinetic energy. It gets to the bottom of the hill. But now that it's at the bottom of the hill, how do we then put some energy back into it? Well, we could use our own kinetic energy. We could push the ball back up the hill. And as we push the ball back up the hill, we are putting our kinetic energy, our energy of movement, back into that ball. And when it gets to the top of the hill, we put that wedge back in place. And all of that energy that we have put into the ball is now stored in that ball again as potential energy. So we can convert back and forth between potential and kinetic energy. Now, here's where we're going to get a little bit nitpicky. So kinetic and potential energy. These are types of energy, and this is a very specific word, types of energy. We're going to see in just a little bit that there's something called forms of energy, and there is kinetic and potential types of each of the forms of energy that we will see. There is stored and motion types of each of the forms of energy that we will see in just a moment.
So here are forms of energy. Chemical energy, which is energy stored in chemical bonds. We will be talking about these in an upcoming lecture. But if that energy is stored in a bond, it is potential chemical energy. If we break those bonds and that energy is released, then that is kinetic chemical energy. Next, let's talk electrical energy, electricity. This is the movement of charged particles. We could have stored electrical energy. That's potential electrical energy. One example of that is a battery. But then once we hook that battery up to something and those charged particles start moving through a wire, well, that is kinetic electrical energy. Next, mechanical energy. This is really what we were talking about a moment ago with the ball. Mechanical energy is directly involved with the movement of matter. That ball at the top of the hill had potential mechanical energy. As it rolled down the hill, it was giving off kinetic mechanical energy. Another example of this is a dam. The water behind the dam that is being held in place has potential mechanical energy. When that dam is open and some of the water starts flowing through, that water is giving off kinetic mechanical energy. And last, radiant electromagnetic energy. Radiant energy, electromagnetic energy, they're the same thing. They're just two different words. And this travels in waves as light or heat. This is a little bit harder to give examples of, but one that I can kind of think of, it's really more chemical energy, but we're going to use it as an example of radiant or electromagnetic. You know those little hand warmers that you can get in the sporting goods area? Well, normally they're just sitting there. They're not giving off heat or anything. So they have potential radiant energy. But once you wave them around, bang them up a little bit, snap something inside of them, whichever type you have, and it starts heating up, well, that heat is now going to be kinetic radiant energy. It's heat. And just like we can convert between the types of energy, we can also convert between forms of energy. Energy can be converted from one form to another, and an example that we have here is becoming less and less common because as we move to the new types of light bulbs, they're a lot more efficient and they work just a little bit differently, but most of us are still able to remember the old style light bulbs. You screw it in and then you flip the switch and electricity flows into that light bulb. It flows through the filaments and they light up. So we are converting from electrical energy into light, which was what? Radiant or electromagnetic energy. But if you let that sit there for a while and you come and unscrew the light bulb, you're going to burn your finger. It gets hot. Why is that? Because when you convert from one form to another, it's really inefficient. And not all of it is converted neatly from one form to another because some of it is going to be lost as heat. It's not really lost, it's just that's another conversion. So heat is produced as a byproduct when we convert from one form to another. Now, one thing about energy is energy, when we convert it from one form to another, all of that energy is still there. The electricity was converted into light, some of it was lost as heat, but the same amount of energy was still there. We did not produce light. We did not create light. We made light from electricity. We converted it. And we also got heat out of that process. Energy cannot be created, and energy cannot be destroyed. It can only be converted from one form to another. But the same amount of energy is always there. So now, switch gears again, talking about matter. Matter is composed of elements. There's lots of elements, and all matter is composed of those elements. Each element is a little bit different from every other element. They all have unique physical properties. Physical properties are things that are measurable, observable. What does it look like? How much mass does it have? Things like that. And also unique chemical properties. How does it behave when it goes through a chemical reaction? How does it interact with other elements? And I've got some examples down here. We've got a diamond, so that's carbon. Carbon is an element. We'll talk a lot about carbon in this class. Chlorine. Chlorine is a poisonous gas. Mercury. Mercury is the only liquid metal at room temperature. It is also highly toxic. Lots of different elements. You do not need to know all of the elements on the periodic table. Anytime you need to know something from the periodic table, one will be provided to you. So you do not have to worry about memorizing anything from the periodic table. These are just there as examples for you right now. But we are matter. Remember, matter is anything that takes up space and has mass. So we're matter, and if matter is made of elements, what are we made of? Lots of elements, but 4 of them make up almost our entire mass. 96.1% of our mass is made of these 4 elements: oxygen, carbon, hydrogen, and nitrogen. Those 4 make up 96.1% of our mass. You do need to know that. You do not need to know that oxygen is 65%, carbon is 18.5%. You don't need to know that. But if I ask you what 4 elements make up the majority of our mass, you should be able to tell me these 4. By the end of this chapter, and especially by the end of this class, you are also going to know that oxygen, its atomic symbol is O. Carbon, its atomic symbol is C. Hydrogen is H. Nitrogen is N. Just because you are going to use these so much, they're going to become second nature to you. So don't worry about, right now, I can't remember that nitrogen is N. I thought that was something else. Don't worry about that. You are going to get comfortable with these because we're going to talk about them so much. Well, 3.9% of our mass is going to be these 9 elements. These 9 elements make up just shy of 4% of our body mass. Calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. We're going to talk about these a lot too, and you will eventually get to where you can tell me the atomic symbol without really thinking about it all too much. Over here, some functions. I'm not going to ask you those functions. And I'm not going to ask you all 9 of these elements, what do they make up, or anything like that. The first 4 are what I want you to know. This is just to kind of give you a heads up, hey, we're going to be talking about these later this semester and next semester. And trace elements. There's a lot of what we call trace elements. These are elements that have presence in our body, but not a lot. They're really kind of used to handle enzymatic activity, or they make up parts of enzymes. Enzymes are things that we'll talk about later. They're things that help a chemical reaction to occur. So these things, I'm not going to really ask you much about them at all, if anything. This is just there to complete the list. All right, very short lecture today. I didn't want to overwhelm you the first day of chemistry, so we will stop there and we will dive into more chemistry in our second Chapter 2 lecture, and I look forward to seeing you then. Please be sure to reach out with those questions as you have them. All right, take care, everybody.